Chapter 6, still, I guess, right? And we've talked in previous sections about internal energy. Internal energy, right? Remember that? And that was the sum of the kinetic energy plus the potential energy of a system. It was also the heat plus the work, right? We talked about what those terms meant and how we calculate those. Now we have a new term, enthalpy. All right, and it turns out enthalpy is going to be defined as the internal energy plus the PV. Okay, internal energy plus the PV. Let's see what we can get from that. By the way, this is going to end up being super useful to us. So it may seem like we're just piling terms on you, but hang tight. Write notes down. Say these words out loud, and I think you're going to find that that you get comfortable with it with enough practice. You definitely will. Okay. So enthalpy is defined as the internal energy. This is enthalpy. Say it out loud. Enthalpy. Say it out loud. This is the, let me go to a different color. Internal energy. Right? You can memorize this. It's true. It's a definition. Enthalpy is equal to the sum of the internal energy plus the pressure times volume. Okay? Well, that's not super useful to us because it's difficult to think of. It's difficult to think of internal energy in absolute terms, but it is relatively accessible to find changes in internal energy. All right, so this is going to be super useful to us. Well, the change in internal energy. Let me go back to red here. Plus the PV. You guys remember what this is? This is the minus work, right? So the change in internal energy plus the PV work is equal to the enthalpy, all right? The change in enthalpy. Okay. Now, since the change in internal energy, say it out loud, is equal to the sum of the heat and the work, then we can just take that, right, and replace it. Okay. So the change in enthalpy is the Q plus, which is heat, plus work, plus P delta V. Well, P delta V is negative work, right? Remember that? So this is minus W. So this ends up being, I skipped a step here for you, right? This, the change in enthalpy is equal to Q plus W minus W, right? And I can do that one in my head. So this is at constant pressure. We know that the change in enthalpy is the heat that is exchanged at a constant pressure, right? So this is something you can memorize. Delta H, I'm just rewriting it, I know, because it feels good to write it, I guess. The change in enthalpy is equal to the heat that's exchanged at a constant pressure. Okay? So let's think about let's introduce a couple terms. An endothermic reaction is a reaction. Watch this. Thermic. Can you hear heat when I say thermic? Okay, so an endothermic is something that puts heat into the process. Okay, or takes heat into it. All right. An exo is something that lets off heat. Can you see that? Can you see exo and lets off? And endo is into. Okay, so endothermic is something that absorbs heat. Okay, and exothermic is something that releases. I think Tro uses the term evolves heat. Okay, a lot. All right. So that's what endo and exothermic reactions or processes are. Let's look at a couple examples. If you have a flame, can you see a flame here? This is a little bit of an ugly picture, but suppose that you can see you see from a stove top burner? Can you see that right there? A stovetop burner? Well, that's letting a flame off, okay? That's a really ugly flame, isn't it? But if you've got a flame going off, it's letting heat into the surroundings. It's releasing heat into the surroundings. Can you see that? And so it's exothermic. All right. On the other hand, something that's a little bit more difficult to visualize is a cold pack. You put this cold pack on your wrist, and that takes heat from your wrist, right? So the surroundings are over here. The system is your wrist. I don't think this doesn't look like it's written right, does it? The wrist is here. It turns out the surroundings are taking heat out of your wrist. Okay, and they're really going into the cold pack, and I guess that's why it's written like that, okay? So the heat is going into the cold pack, and you can feel the heat leaving your wrist, and so it feels cold, all right? Okay, so in review, the value of the change in enthalpy for a chemical reaction is the amount of heat absorbed or evolved in a reaction, for a chemical reaction, in the reaction under conditions of constant what? What did we say? Conditions of constant pressure. The value of the change in enthalpy for a chemical reaction is the amount of heat absorbed or evolved in the reaction under conditions of constant pressure. In other words, I know we just said that a minute ago, but in other words, the change in enthalpy is equal to heat, right, at a constant pressure. Okay, now you fill this in. An endo or exothermic reaction has a positive delta H and absorbs heat from the surroundings. Is that endo or exo? So think about this. If you have, remember that the change in enthalpy is equal to H final minus H initial, right? Because that's what change means. So if this is greater than 0, let's say, just a minute here, greater than 0, it's positive, right? That means it has more heat in the end, or more, I should say, enthalpy in the end, right? It means it absorbs, okay? So what is this? This is an endothermic reaction because the final has more heat than the beginning, right? So, and it absorbs heat from the surroundings. Endothermic reactions generally feel cold. Okay? Watch out for this, though. They generally feel cold. All right, so what's this? A blank endo or exothermic reaction is a negative delta H. And what that means, remember, delta H is equal to the enthalpy final minus enthalpy initial. And if that's less than 0, that means that this is smaller, right? So it means that if it goes from big to small, let's make up a number, okay? I'm going to say 11 to 8, right? Then that means that it lost. Can you see that? Started out with 11, that's initial, goes to 8. Making up numbers here to give myself something that's going to give me something negative, okay? So if it's going to be minus 3 in this case, and that is going to be an exothermic reaction because it's letting off heat to the surroundings, okay? And exothermic reactions generally feel warm. Can you picture a flame there? Suppose it's a candle, okay? All right, so that's going to be an exothermic reaction, and yes, it feels warm. Don't touch it. All right, so let's look at some specific examples. Identify each process as endo or exo. Indicate the sign of the change in enthalpy. So sweat evaporating from the skin. Is that sweat? Is it taking heat in? Right? Final minus initial for A is the sweat evaporated sweat, which I guess is just water vapor, I guess, at this point. Oops, no, it's the other way around. Sorry, it's evaporated in the beginning. And it's in the beginning it's sweat, right? And it becomes evaporated. Is that gonna take heat in from your skin or let heat into your skin? Well, it's taking heat from your skin, right? And so the sweat itself is, let's see, the sweat, if this is I gotta stop and think for a second. The enthalpy of the sweat is going to increase, right? So it's going to go, let's say, from 8 to 11. So this is going to be positive 0, right? It's actually going to be 3. Now, if you're looking at it from the skin's perspective, it's losing energy to the sweat, right? So if you're looking from the skin's perspective, is the skin losing heat or gaining heat in this process? It's losing heat, right? That's the whole point. So in the beginning it might have 8, 11, and then it might have 8. Are you okay with me using 8 and 11? I'm just picking numbers out, right? So it's easier for me to see. That's definitely going to be 0, or rather less than 0. It's going to be negative, okay? So if we're talking about the skin, then delta H is less than 0. If we're talking about the sweat, delta H is greater than 0, right? And I can't tell which one they're looking at here. Sweat evaporating from the skin, probably talking about the sweat. I don't know. All right, water freezing in a freezer. When the water freezes, does it lose energy or does it gain energy? So delta H is equal to the final enthalpy minus the initial enthalpy, and it's definitely going to be losing, right? Water is losing energy. This is going to be negative 3. So for B, delta H is less than 0. It is exothermic, right? Here's a trick one though, right? Remember we said exo typically feels hot, but if this is freezing, does it feel hot? No, it doesn't. It's still exothermic though, right? Because it's losing heat to the surroundings. Okay, and C, wood burning in a fire. You know what? I'm going to let you do that one on your own. I'm going to do it with you. Okay, I need to go. My washing machine's broken. I got to pause the video here because it's about to start shaking. Just a moment, please. Be right back. It still works, but it's got something loose in there, and when it starts spinning, it honestly sounds like the house is going to fall down. Okay, so I could edit that out, I guess, but you know, that takes time, and I'm afraid I'd rather get this video up and move on to the next video. So, all right, I know I'm going to get it's going to bother somebody. All right, so let's look at this. Let's look at this now in terms of chemical reactions. So this is good news because this is usually where we're going, right? An LP gas tank in a home barbecue contains 13.2 kilograms of propane. All right, so not even sure where we're going yet, but let's do this. The mass in kilograms. I'm always concerned about moles, right? So let's do the mass in kilograms first. 13.2, and then this is going to be a lot of grams, so it's going to be 13.2 times 10 to the, times 10 to the 3, right? Because kilograms, there's my kilo. 13.2 kilograms. Okay. Now, I'm going to get the moles before I even go anywhere. So it's 3 times 12.01 plus 8 times 1.08. I think I can do this one in my head. 36.03 plus 8.64. 8.6476 44.67, but I can't do the next part in my head. 44.67 grams per mole, right? So how many moles is that going to be? Well, it's going to be 13.2 times 10 to the 3 divided by 44.67, which gives 295.5. Is that possible? All right. 295.5 moles, okay? All right, calculate the heat in kilojoules. Yeah, and this is good. Okay, so we need this, right? Because we have the change in enthalpy of the reaction. What this means is this is minus 2044 kilojoules, and that's, watch this, per mole of propane or per 5 moles of oxygen, right? Or per 3 moles of carbon dioxide. So I'm going to say, watch this, per mole of propane. Okay, that's perfect. I'm glad we did this now. Okay, so the change in enthalpy of the reaction is equal to minus 2044 kilojoules. And they want to know, calculate the kilojoules associated with the combustion. All right, great. So what this means is we've got 295.5, watch this, moles of propane. And I know that I let off 2,044 kilojoules for every mole of reaction, but there's only 1-to-1 of this, right? So it's per mole of propane. Can you see I've got 1 mole of propane here? So it's going to be 1 right there. And this is going to be then divided by 2044 is going to give me 0.144, let's see here, 0.14 just a second here. Looking at my notes, and that is going to give me I got something wrong here. Let me look at this. I got something wrong. 295.5 is going to give me, this just doesn't look right, minus 0.144569 kilojoules, right? So I've got that many moles. Let's look back here. 36.03, that's right. That's 0.008. You know what? That's a problem here. This is 1.01. It's not 1.08. It's 1.008. That's a mistake here. Okay, so let me just calculate this again. Crud. All right. 13 point. Wait. I'm going to calculate that formula. Wait again. 3 times 12.01 plus 8 times 1.008 is 44.09. Okay. 44.09. And this is 44.09. And so what I'm going to do now is say that I've got 13.2 times 10 to the 3 divided by, and that gives me 299. A little bit different, not a lot. 299.36 moles, right? Times, now I'm going to come down here and multiply it times negative times 2044. Yeah, I'm not sure what I was doing there. Okay, so turns out that I don't know what this. Where's this number come from? Don't even know. That doesn't make any sense. You see this 300 times 2,000. It can't give me that. That makes no sense. But when I saw that made no sense, we go back looking at this. I saw another mistake, which it turns out hardly made any difference. But this goes to, watch this, 611,892 kilojoules. Wow. Are you serious? Really? 893 kilojoules. Okay, so this is 6 point, to go into 3 sig figs, 0.12 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5 kilojoules, and it's negative, right? Okay, so there's my answer. And let me look at my notes here. Yeah. Okay. So there's my answer. I'm not exactly sure how I got this answer. Can you see why this would be a problem for me? Stop for a minute. If that's frustrating, or especially if you feel a bit overwhelmed, it would be a good exercise to go back and look at this. This is about 300. This is about 2,000, right? And 300 times 2,000 cannot give you 0.14. I don't know what I did with my calculator, but that made no sense at all. All right. So then I went back looking, found this other mistake. It's 1.008, not 1.08. All right. Wow, that's ugly, isn't it? I think that's it for this section.